In this video, we are going to review the properties of exponents and radicals. And this review should help you be ready for your college algebra course. As you're watching the video, please feel free to pause, try problems on your own. You should be taking notes. What you shouldn't be doing is just sitting on the couch and letting the video play, okay? So be engaged in the video if you want to learn this material. First up, I have here on the screen the basic laws or properties of exponents. I'm not going to read each one of those to you, but you can take a screenshot of that or refer back to that if you need a refresher on any of those. What we're going to do is go ahead and jump into the examples where we apply those rules. So the first set of problems here, we are going to simplify. When we're simplifying, we want everything to have positive exponents and any rational expressions to be reduced. So let's take a look at this first problem. What we have right here, even though there are parentheses around it, notice these parentheses don't have any exponents on the outside. So really what we have here is one big multiplication problem. All these things are multiplied together. Multiplication is commutative. That means it can be written in any order. So we could kind of regroup things. We could say that's 2 times negative 4 times x cubed times y squared times y cubed. Notice I haven't changed anything. I just rewrote the order, and I can do that because everything here is multiplied together, okay? So now I can go ahead. I kind of group things together on purpose. I put my two numbers out front. So 2 times negative 4 is negative 8. And then I grouped my x's together when we have same bases, matching bases. So these both have an x in the bottom. In order to multiply those together, we add their exponents. So here we have x to the first. If there is no exponent, it's to the first power times x to the third. So this becomes x to the 1 plus 3 or x to the fourth power. Same for our y's. I wrote them next to each other so we can see this very clearly. Y squared times y cubed, matching bases. Multiplication means we add those exponents. 2 plus 3 is 5. So that one is really applying basically this first rule that we have right here. Let's do some more. Now look how this one differs from our first example. We have two sets of parentheses again, but now we have those exponents out there. We can't just ignore those and start going crazy, okay? We need to apply those exponents to everything inside the parentheses. So what we've got going on here is 4 squared x to the negative 11th squared, y cubed squared. Basically, I applied that exponent to every factor inside the parentheses. And that is, which rule is that? That's this rule right here, this property. And I'm going to do the same thing with the second set of parentheses. So we have x to the 7th, which is raised to the negative 3 power, y to the 9th, which is raised to the negative 3 power. Next up, we can start simplifying all of these stacked exponents. Well, first of all, 4 squared. Remember, that's not 8. It's not 4 times 2. 4 squared is 4 times 4. 2 4s multiplied together, so that's 16. And then when we have these two exponents stacked here, in order to combine them, we multiply them together. So this would be x to the negative 11 times 2, which is negative 22. Again, stacked exponents here. 3 times 2 is y to the 6th. X to the 7th raised to the negative 3. So multiply those exponents. And y to the 9th raised to the negative 3. Now, just like our last example, we do have some matching bases. Here's an x and here's an x. So let's put them together. Remember, we're going to add those exponents. So that's negative 22 plus a negative 21. So that's negative 43 for our x. And the y's, we're going to add those as well. We have y to the 6th plus a negative 27, which is negative 21. So our final thing we want to do, we've done pretty good so far, reducing things, simplifying things, but now we want to address those negative exponents. And we have our negative exponent rule up here at the top. Anytime we have a negative exponent, what we do is we are going to remove that negative sign and kick that factor or that piece down to the denominator, or move it to the opposite place. If it's in the denominator, it comes out. If it's not in the denominator, it goes down. So the 16 is just a plain old 16, so it's going to stay on top. But that x to the negative 43rd, that negative exponent really means that's an x to the 43rd in the denominator. Same thing with that 21, x to the positive 21. The exponent becomes positive when I move it down below. And then this would be what we consider our fully simplified answer. Notice I didn't move the 16 down. It doesn't have a negative exponent, so it stays right where it is. Next up here, we have another thing we can simplify. We can kind of start doing some canceling here. Notice we have a 12 on the top and a 9 on the bottom. They share a common factor of 3. So if I divide a 3 out of both of those, now I have a 4 on top and a 3 on the bottom. I have some x's on the top and x's on the bottom, and that's one of our properties also. When we have matching bases with division, we just did matching bases with multiplication. When we have matching bases with division, we subtract those exponents. And we'll do that for our x's and our y's. So we have that 4 and that 3 from reducing our 12 and our 9. We have x to the 8th on the top and x on the bottom. So that means we are going to have x to the 8 minus 1, or x to the 7th. Does it go on the top or the bottom? Well, it's a positive exponent, so it goes up top. Similarly with our y's, we have y to the 3rd on the top minus y to the 4th on the bottom. You always subtract the top exponent from the bottom. So that gives me y to the negative 1. Since that's a negative 1, I'm going to take that y and put it in the bottom, and then it becomes a positive 1. Okay, so I could have written this first. Okay, that's what I came up with when I do the subtraction. But since it's a negative exponent, I went ahead and simplified it by putting it into the denominator. Okay, next example, just trying to combine as many of these different rules as possible and demonstrate them for you. There's a couple different ways we could approach this one. We could take that negative 3 exponent and apply it to everything inside the parentheses, okay? But I think this one will be a little easier if first we take a look at what's in here and see if we can do any simplifying before we start applying that negative 3 exponent. So I'm going to leave that alone. We'll talk about that in a minute. Look inside here. Well, there's a 5 on top and no other coefficients, so I can't cancel that with anything or reduce it with anything. It's just going to stay there. My x's, I have x's on the top and the bottom, so I can subtract those exponents. X to the 3 minus 2 is x to the 1st power. And same thing with our y's. We can subtract those exponents. 2 minus 5 is negative 3. So y to the negative 3 means I'm going to have y cubed on the bottom. Now I'm ready to apply that exponent. So I have 5 to the negative 3, x to the negative 3, and y cubed to the negative 3. Stacked exponents again on the bottom, so I'm going to multiply those. And then we got to deal with all those negatives. We can't have negative exponents in our final answer. Everything is a product here, so those negative exponents, we can just flip things on our fraction. So 5 to the negative 3 up top is equivalent to 5 to the positive 3 in the bottom. X to the negative 3 up top is equivalent to x to the positive 3 in the bottom. And y to the negative 9 in the bottom becomes y to the positive 9 in the top. And then finally, 5 to the 3rd power. We shouldn't leave it like that. That's something we can calculate. Use your calculator. Let me show you the exponent button on your calculator. So if you have the TI 30XS Multiview, which is a great little calculator, And on a lot of other calculators also, the exponent button looks like a little upside down V. It's this button right here. So if I want to calculate what 5 raised to the third power is, that's 5 times 5 times 5. There's my base. Then I use my exponent, and you can see my cursor even popped up to show you it's an exponent. And then I hit enter, so that is 125. So our final answer, y to the 9th over 125 x cubed. Next up, we're going to talk about radicals, but before we do that, I want to point out one more thing. The way we did this, we took our exponent and applied it to everything in the parentheses. We can only do that if there is just a single term inside the parentheses. And let me show you what I mean by that. If we have x times y squared, that is indeed equivalent to x squared times y squared. Makes sense. However, if you have x plus y, look, a plus sign in between. These are not multiplied together. We now have two separate terms in the parentheses. Squared, that is not ever, no way equal to x squared plus y squared. Not true. This is a super common mistake. Well, why isn't it true? Well, let's write it out. X times y, x plus y squared is x plus y times x plus y. That's what we mean when we square something, right? We multiply it together 2 times. And to figure this out, we can't just say it's x squared and y squared. We have to FOIL this out. We get an x squared. We get an xy. We get another xy. And we get a y squared. So you can see it's actually equal to x squared plus 2xy plus y squared. Okay, you can only apply that exponent into the parentheses if everything is multiplied or divided together. If you have multiple terms, you cannot just take that exponent and put it on the different terms in the parentheses. Okay, so that was a little review of exponents. Next up, we're going to look at radicals. Okay, here's what I'm talking about with radicals, that funny little sort of check mark shape. And just so we have our terminology straight, when I say the word radical, I'm referring to that symbol. Okay, the radicand in this little example right here is A, but it's whatever is under that symbol, whatever's underneath there, that's called your radicand. And maybe more important is the index. In this case, the index is n. It's going to be that little number that goes in front of the check mark. That is called our index. So basically, when we have just this with no number here, that's a square root, which is sort of the opposite or inverse operation of squaring something. Okay, so if 3 squared is equal to 9, then the opposite of that, the square root of 9, is equal to 3. We're looking for a number that when we multiply it by itself, okay, 2 copies of it multiplied together give us this result, okay? So when we are asked to simplify radicals, here's some steps we can take. We're going to do it by hand and on our calculator both. First, write out the prime factorization of the radicand. Okay, so that means take the number that's under the radical, in this case, it's a 49, and write out the factors until you end up with only prime numbers. Okay, well, the factors of 49, there are only 2. 7 times 7, that's it. You can't break it down any more than that because 7 is a prime number. So 7 times 7 gives us 49. Since this is a square root, we don't write the index 2 when it's a square root, but it's implied, it's understood to be there. So anytime we look at the index, it's 2 on a square root. So anytime there are 2 copies of the same factor, that factor gets to come out of the radical, so that the square root of 49 is equal to 7. Okay, we're looking for pairs of factors because this was a square root. Let's do another one. Factors of 98. Well, I don't know them off the top of my head. Let's see. I know it's an even number, so it can be divided by 2. There we go. 2 times 49 gives me 98. 2 is a prime number, so that one's done. But 49 can be broken down again, 7 times 7. There are all my factors. Again, not written, but we know as a square root, our index is 2. So we are looking for pairs. Here's one pair of 7s. So the 7 gets to come out of the radical. However, we don't have a pair of 2s. We only have a single 2, so that one has to stay inside. So there is our simplified radical for the square root of 98. Notice our simplified radical here didn't even have a radical in it. It simplified all the way to a whole number. Let's look at our next one, 180. Well, let's see. I know that one way we could write that would be 10 times 18. 10 can be broken down further into 2 times 5, but 2 is prime, so that one's done. 5 is prime. 18, you can break it down a few different ways. How about 3 times 6? 3 is prime, so that one's done. 6 is 2 times 3, and they're both prime. So if I multiplied all those circled numbers together, I would get 180 as my answer. Again, this one is another square root, no index there, so we know it's 2. So we are looking for pairs of numbers. I have a pair of 2s, so the 2 gets to come out of the radical. It's like you got freed. Yay! There is also a pair of 3s. So a 3 gets to come out of the radical also. Those two are going to be multiplied together eventually. And then the lonely 5 has to stay inside because we don't have a pair of 5s. We would simplify this further. 2 times 3 is 6 times the square root of 5. So there is our simplified radical. Now, if you have the multi-view calculator, it can actually simplify radicals like this for you. The square root is right here. It's this little symbol on top of x squared. So to get to any symbol that's above a button, you hit the second key and then that button. So the square root of 98, I can type it in there and boom, there's how it simplifies. 7 square root of 2. I can do the 180 that we did as well. The square root of 180 is 6 times the square root of 5. If you don't have this calculator, or sometimes if you get numbers that are too big, you do have to know how to do it by hand, but the multi-view can help you with a lot of those. Okay, this time we have the cube root. Oh, that's exciting. We changed. It's not a square root anymore. It's a cube root. So we're going to do it the same way, though. We're going to write the prime factorization of 72. I know 72 could be written as 8 times 9. 8 can be broken down in 2 times 4. That one's done. No more breaking down. But 4, we can do it again. 2 times 2. And 9 is 3 times 3. With square roots, we were looking for pairs of numbers, but with the cube root, we are looking for triplets. We need 3 copies for it to come out of the radical. So we have one set of 2s, so a single 2 comes out. It is still a cube root, and what stays inside is 3 times 3, or 9. So this would be 2 times the cube root of 9. And one more, because why not? The 4th root of 288, that's a doozy. Looks fun. So 288, again, we have to break that down. I don't know the factors of 288 in my head, but I know it's even. So I can start there. So 2 times 144. And let's say I don't know the factors of 144, so I would just divide it by 2 again. I get 72. 2 times 72. My 2's are both done. They don't break down. 72. I can start to do that one by hand because we just did it. Okay, so there's all our factors. All those, I like to circle them so I don't lose them in there and all those numbers. The circled ones are what we are looking for. And this time, remember, it's a 4th root, so we are looking for sets of 4. 1, 2, 3, 4. One set of 4 means that 1, 2 comes out front. Anything else has to stay inside. Don't lose your index. If it started as a 4th root, it has to remain as a 4th root. Inside would be 2 times 3 times 3. If you multiply those all together, that is just 18. Let's do one more, just for fun. A write-in. How about this? How about the cube root of 320? Okay, so we'll do it the same way. We'll make our little factor tree. 320 is 32 times 10. 32, 8 times 4. 8 breaks down. And these 4s break down. And my 10 breaks down. Okay, so cube root, the index of 3, means we are looking for triplets. 1, 2, 3. There's one set of 2s that gets to come out. Oops, I don't want a highlighter. I want a pen. That means one set of 2s gets to come out. But look, I have another set of 2s. Boop, boop, boop. There's another triplet. So another 2 gets to come out. Remember what we multiply these together. And then that lonely 5 has to stay inside. So 2 times 2 is 4 times the cube root of 5. Okay, we can also do this simplifying of radicals with variables. We were just looking at numbers so far in those examples, but sometimes we'll have variables in there. So basically, we're going to break this down. The 324, we're going to do the same way we just did the other examples, and then I'll show you what to do with the variables. So let's do it again. 324, how do we break that down? 324 divided by 2 is 162. I don't know that one either. I'm going to use my calculator. I don't do a lot of math in my head. 81. 2 times 81. 81 I can do. That's 9 times 9. Oops, but 9 is not done. 9 can be broken again into 3 times 3, and that 9 is also 3 times 3. You could always check yourself by multiplying all those circled numbers together. But that tells us what to do with the 324, right? It's a fourth root, so we are looking for a set of 4 factors. So here's one set of 3s, so a 3 gets to come out, and then the 2 times 2, which is 4, has to stay inside. So let's jot that down. The 3 gets to come out. Again, we had 4 3s here, but when it goes through the radical, that we talk about how many groupings we have, not how many 3s we had. So we had one single 3 comes out, and 2 times 2 or 4 stays inside. So that takes care of that number. Now, what about this part? What do we do with the fourth root of a to the 20th? Well, we want to know how many sets of 4a's are under that radical. So the way we do that is actually division. How many groups of 4 are in 20? This one divides out evenly. There are exactly 5 groups of 4. So that means a to the 5th gets to come out of the radical. And then for the b to the 17th, we also need to figure out what the fourth root of b to the 17th is. Again, how many sets of 4 are in 17? So we do a little division, the index into the exponent, 17 divided by 4. Well, that's 4, but that only makes 16, and we have 1 left over. So when we do this division, our answer tells us how many get to come out of the radical, and the remainder tells us how many are trapped inside, b to the 1st. Just 1 is stuck inside. I do need to put all of these back together to make my final answer. So outside of the radical, we have 3, a to the 5th, b to the 4th. And inside the radical, we have 4b. There is our simplified radical. And let's do one more, just for fun, of course. Again, we'll break it down. The numbers I do with my factor tree. 54 is what? 9 times 6. So we get some 3s and a 2. So that means, again, we're looking for the cube root. So here's one set of 3s. So the 3 gets to come out, and this 2 stays inside. What about the x to the 10th? How many sets of 3 are in 10? Well, there are 3 full sets, but that only makes 9, so there's still 1 left over. So x cubed gets to come out, and 1x has to stay inside, x to the first power. Then we have the 14, y to the 14th. How many sets of 3 are in 14? That would be what? 4 sets would make 12, but that means there's 2 left over, 2 that are not complete sets. So y to the 4th from our answer gets to come out, and y squared from our remainder has to stay inside. There is our simplified radical. One other thing to talk about in this section are rational exponents. Rational basically means fraction. So a rational exponent is an exponent that's a fraction. And the thing you need to keep in mind are these two definitions right here. A fraction exponent is the same as a radical. It's just two different ways to write the exact same thing. If you have a 1 on the top, that means you just have an a, or whatever your base is, under the radical. The denominator, the bottom, becomes the index. Okay. If you have numbers on the other than 1 on the top and the bottom, the top tells you your exponent, the bottom tells you your index. So when we are asked just to rewrite here, we're not doing any math, we're not doing anything complicated. The exponent, which is the 5, that's going to become the top of my fraction exponent. And the index, the 3, that is going to become the bottom. This is equivalent to that radical. What about this one? We have a radical. What's the index here? If you don't see an index, the index is 2. It's implied square root. So we have y raised to the 7th. There's the exponent over 2. There's the index. 7 over 2 is my fraction exponent that's equivalent to this radical. We can also go in the opposite direction. Here we have x to the 3 halves, which is equivalent to x cubed. The top is the exponent, and a square root, the bottom, is the index. You don't have to write the 2 in there. If you do, it's not entirely wrong. It's just not the normal way we write it. But these two are equivalent. And finally, here, even if you have an expression in the parentheses, it still works the same way. Since there are parentheses, that exponent applies to that whole expression. So we're going to have 1 plus x to the 5th. The numerator, the top, determines your exponent. And we are taking a cube root. The denominator determines your index. So when you see a problem like 36 to the 1/2, that may seem confusing, but if you rewrite that as a radical, that's just the square root of 36, which is probably one you know in your head. 6 times 6 is 36. Again, 64 to the 2/3, maybe not real straightforward to think about when you have it written like that, but we know now that this is equivalent to 64 squared and the cube root. Now you can do the cube root first or the squared first. It doesn't matter. Either way, your calculator can do that for you. If we want to do a cube root on our calculator, we have to type the index first. And then we use that second button again to get this radical with the x in front. This allows you to have any index on your radical. And then we would type the 64 squared inside. And that becomes 16. Ooh, we got a negative exponent. What's that mean? You remember? Negative exponent means this is equivalent to 1 over 25 to the 3 halves. I moved it to the denominator and made it positive. Now we can deal with that fraction exponent, which would be the square root of 25 cubed. Top becomes the exponent, bottom becomes the index. The square root of 25, I can do in my head, right? Square root of 25 is 5. And then 5 cubed, can you do that one in your head? 5 cubed, I think, is 125. We're going to skip that one. And so that brings us to the end of the video. If you have any questions, please contact your instructor.